So welcome back. Problem set, I got overshot here. Problem set 3 is now posted. It's due next Wednesday. On Friday is the first midterm exam. I probably haven't mentioned yet, or don't recall mentioning yet, the idea of practicing. Why is it so loud? Practicing for the exam by taking old exams. You'll find if you go on the website for this class on my computer, you'll find under resources lots of old exams, including lots of old midterm ones. And I encourage you to take the old exams. Don't look at the answers to the old midterms. That's not the same experience as actually taking them. And you'll learn what sorts of questions how I ask questions, what sorts of questions I ask. I sometimes steal my own questions. Sometimes I rewrite them and then discover that I wrote it better 2 years ago. I invent the same questions over and over again. It's I think, a decent learning experience, the act of taking the old exams. So I encourage you to do that. 30 questions, multiple choice, here in this room. What else? Bring a pencil, but that's about it. Any questions about homework, exams, any of that stuff? Okay, so back to talking about static electricity. And I told you last time that we observe in nature a conserved quantity known as charge. You can have positive amounts of it, negative amounts of it. Two positive amounts of charge repel each other. This has not been a problem in the past. Two negative amounts repel each other, but two a positive and negative attract one another. The force gets weaker with distance. Now it's dropped too low. Can't win. Hello, hello? Hello, hello? There are things they can do from outside the room and may be doing. Okay. Too much technology. What else? Oh, the forces fall off with distance quite rapidly. They go not in proportion to distance, but in proportion to distance squared. So doubling the distance between two charges reduces their force by a factor of 4. It plummets. The world is made up of things that are electrically charged. The subatomic particles, they just come to us. We didn't, who knew? There they are. Electrons are negatively charged. The protons that constitute part of the nucleus of an atom are positively charged. There are some exotic particles around that have charge as well, that show up with, for example, cosmic rays. But for all practical purposes, all the positive charge you ever encounter really resides on the protons in the nuclei of atoms, and all the negative charge you encounter in everyday life is on the electrons. Any questions about charge stuff? Okay. And the origin of static electricity, in most cases, is the chemical dissimilarities between materials. When two materials touch each other that are chemically dissimilar, they're not the same material perfectly. They tend to exchange charges, in particular electrons. One of them comes off with more than its fair share of electrons and therefore is negatively charged, and one of them comes off bereft of and down there in the positively charged territory. Where I finished off last time was talking about that a charged object, so an object that's acquired, say, positive charge just because of its contact with something else over the course of the past 10 minutes, that positively charged thing will attract any other object in the room. And even those other objects, any other non-positively charged object. The reason for that is because the positively charged, let's make it a sock. The sock, when it goes over near a wall, for example, it electrically polarizes the wall. I put the word electrically in there because you can polarize things in other ways, politically. No, electrically polarizing the wall, that comes about when you take advantage of the fact that the wall's got positive charges in it, lots of them, zillions, and negative charges in it. They happen to be in equal quantities, therefore they can perfectly cancel. And when I'm talking about adding them up, I'm talking about adding up the little fundamental units, the little electron charges and the proton charges. When you add them up, they add up to 0. But if you bring your little positive sock up nearby, you coax the negatively charged particles a little closer to you and the positively charged particles a little farther from you. You create this slight displacement of charge within the otherwise neutral wall, and the wall is now electrically polarized, meaning it has no net charge in this case, but it has a positive end and a negative end, like poles. Because you're causing this with your positively charged sock, the negative pole's near you. The positive pole is away from you. And there's a little extra attraction to the negative pole compared to the repulsion from the positive pole. And the sock clings. So you've seen this effect with just stuff. You get charged stuff around packing materials in particular, which is sort of one of the topics for the problem set. You know, the foam peanuts or something like that. They're just like, you can't get them off you. They stick to you. As soon as they acquire a charge, which they do very easily, they just stick on anything that they can polarize. And they're hard to get rid of. I finished the day talking about these negative ion generators, which I'll revisit briefly. The most primitive way of cleaning the dust in your house, smoke or whatever you want to clear out of the air in the house, the simplest way, but with a downside, is to spray. And we'll talk later about how to spray charge out into the room air. So you can spray positive charges into the room air and let them. They will naturally. A positive charge will polarize a dust particle and stick to it. And so now you got a positively charged dust particle, and it will go and polarize the wall and stick to it. And so if you want to clean the room air, just spray one charge, whatever charge you like, spray it out into the room air. It will stick on all the dust particles and smoke particles because of polarization effects, which will then in turn stick on the wall and your carpet, your hair, your furniture, because of polarization effects. So it works great. The downside is, after a couple of years of using this, you discover nothing's white anymore in your house. Everything has a layer of crud stuck on there because of these effects. Swiffers, actually, just on the side, the Swiffer claws that pick up everything, there's charge on it. They put charge on it at the manufacturing, so it's got charge sitting on there on the surface. It picks up everything because of polarization effects. Anyway, that approach to cleaning is kind of big downside. The more sophisticated way of cleaning the dust and smoke out of the room air is what's called an electrostatic precipitator, invented maybe 100 years ago by a guy named Cottrell, who made a fortune and then gave it all to a nonprofit called Research Corp. Anyway, the idea is this: put the charge on the dust particles and give them a destination to go to. Put an opposite charge nearby. So instead of just spraying the positive charge out into the room and letting everything stick to the walls, spray positive charge out and then give them a nice negative charge to go to. The reason I'm mentioning this, I used to use this as a topic sort of at this stage in the class because electrostatic precipitators are super useful. They have shown up in household use, but they're not in vogue at present because they tend to make a little bit of ozone, which is its own issue. But in an industrial setting, you can suck the dust and coal, things like coal-fired industry, for example, but any smokestack industry. Prior to 100 years ago, the smokestacks blew out not just steam, but they blew out smoke. They were called smokestacks for a reason, because once you make these tiny particles, it's hard to get them out of the air. They're held aloft by air resistance effects that are really strong for tiny particles, and you just can't get them to come out. They will not fall out because of gravity, too much air resistance. So how do you get them out? Well, you pluck them out with electric effects. And they use these electrostatic precipitators. They put the charge on all the dust particles, and then they give them an opposite charge to go to, and it just yanks them right out of the air. And so you've grown up in an era where when there's a smokestack belching something forward, the only thing that you'll see come out of it is, where you see it with your eyes, is steam, right? You see, or water vapor coming out. You've probably rarely seen plumes of black, disgusting true smoke and ash come out. Exceptions being cars and trucks. You do see them belching out stuff that's really not nice to see. They could pluck that out with electrostatic precipitators if that were, it could be done. Anyhow, 100 plus years ago, that was not true. Certain parts of the world, until fairly recently, that was not true. There's probably still not true places. That there are places that are just obliterated with smoke, and that's in this country, most of that was wiped out by electrostatic precipitators. Remarkably effective. Okay, enough said about that story. Okay, so polarization effects are done with that. So on to another phenomenon that you probably have noticed with clingy clothes, say, coming out of the dryer, that when you pull them, there's a sock stuck on a shirt. When you pull them apart, something happens. You start hearing snap, crackle, pop all of a sudden. I hope this is familiar to you, like what was that? Well, that comes about when you take positive charge and negative charge. When they're very close to each other, they have some degree of sort of, I'll anthropomorphize everything as I usually do, some degree of satisfaction of being near. The positive charge is near the negative charge. That's good. It keeps the positive charges on the sock happy and the negative charges on the shirt happy. When you pull them apart, the situation changes. All the positive charges on the sock are all near each other, and there's no negative charge in sight. The sock is way over here. These guys became a whole lot more unhappy. The repulsion becomes much more important to them. Is that followable? This is a real hand-wavy version of what I want to do more carefully in a minute. So the act of pulling the charges apart, positive and negative, separating opposite charges, changes things in an interesting way. They become much more, I'll just call them active. They don't like this. And they are more desperate to get back together again. They create sparks and stuff like that for reasons I'll come to in a minute. So why is this? It turns out that it's an energy issue, and it's a potential energy issue. It's an energy stored associated with electric charge. An electric charge near another electric charge, positive or negative. As you move them around, let's make them both positive charges. And then we'll start with them way far apart. And let me bring them toward each other. Well, because they repel each other, this is not an easy task. I have to shove them toward each other. I have to do work on them in the process, because I push them together and they move together. That's work. So in pushing them together, they're not speeding up or anything, but they are taking work out of me. Where's it going? It's going into the forces between them. Remember, that's the generic recipe for there being a potential energy. They're in a form that's known as electrostatic potential energy. That is, the energy stored in the forces between or among or within charges. Okay? So it's similar to a gravitational issue. Gravitational potential energy came from pulling, say, a ball away from the Earth. I stored energy in that force. In this case, I'm not pulling them apart, I'm pushing them together, but nonetheless I'm storing energy in it. So there's electrostatic potential energy. Okay, so if we go back to the situation with the positive sock and the negative cloth, and I hope you can live with my invisible animations here, or cartoons. As I pull the positive sock off the shirt, and the shirt off the sock, that involves work as well, right? Because they don't want to come apart, they like each other, so I have to drag them the whole way. Where did that energy go? Well, it's stored again in the forces between them. In this case, they're attractive forces. So the electrostatic potential energy is increasing as I do this. And the amount of charge didn't change. The sock is still the sock. I'm holding them there with rubber gloves or something, so I'm not exchanging charges with anybody. I don't know. And the energy went up, the charges are the same. So the energy per charge went up. If you sort of assign to each charge a little bit of energy, a little bit of this electrostatic potential energy, it increased. Well, that idea of electrostatic potential energy per charge has a name. It's called voltage. You've heard this your whole life, voltage, lots of volts, no volts, ran out of volts, whatever. It's, you can use it casually in all sorts of ways that make no physical sense. But what does voltage measure? It measures the electrostatic potential energy per unit of charge, where you get to measure, you pick your unit. It can be one fundamental charge, the charge on an electron. Or it can be one of the conventional charges of the metric system, the SI system, known as the coulomb. And if you look at how much, suppose you pull the charges apart and you've got 1 coulomb of positive charge sitting on the sock, and I told you that's a lot of charge, but let's let it happen anyway. You've got a 1 coulomb of positive charge sitting on that sock, and in getting it to this point, and where we started from is a little messy, so I'm not going to dwell on that. To get to this point, suppose I did 1 joule of work to get it to that point. Then I've got a coulomb of charge sharing among them 1 joule of energy in the form of electrostatic potential energy. That sock has a voltage of 1 volt, 1 joule per coulomb. That's a volt. That is what a volt means. It's the energy, it's energy per charge, in this case, 1 classic unit of energy, the joule, for 1 classic unit of charge, the coulomb. So that's what 1 volt is like. If it took me 100 joules of work to drag it away, still 1 coulomb, now it's 100 volts. And what else do I want to say? Oh, what I want to say was that it is a property it characterizes a location in space. So the voltage of the sock and the place where the sock is, that is 100 volts in my most recent version. So if it's at 100 volts, that means that if I let 1 coulomb leave this location for some destination where it has no energy left, and my favorite choice for that is just like the distant stars, just let it go away. So you take the 1 coulomb, let it go away, get rid of all of its electrostatic potential energy. It will, in the process of leaving, release 100 joules of energy. As its positive charge leaving a positive location. It hates being on that positive location. It loves to leave. It's pushed away by all its like charges. And it does 100 joules of work and off it goes. So that's what a location at 100 volts means. Is that okay? So far, at least? Or questions about that? Yeah, Gabby. Say again? Joules and volts are not quite equally each other, because a joule is a unit of energy and a volt is energy per charge. You have to divide it by the amount of charge you have in mind. So 100 volts, a 100 volt ball here means that there are 100 joules available for you for every coulomb that's there. If you take 1/10 of a coulomb away, you don't get 100 joules, you only get 10. If you take 17 coulombs of charge away, you get 17 times 100 joules of energy. And so this starts to give you an idea of, if we suppose the electric outlets are a little more simple than they are, we'll come and deal with them later. But household electricity is delivered at what is nominally listed as about 120 volts. So I hope that's familiar to you, that you have some sense for what the voltage is of household current. These ordinary electric sockets with the 2 slots in them. That's nominally delivers power at 120 volts, which means that, and I don't want to get too complicated in it, but one of the wires is at 120 volts, let's say, and the other one's at 0. And if you take 1 coulomb out of that outlet at 120 volts and let it go back into the 0 volt place, it will have, in the process, left energy behind. How much? If you took 1 coulomb at 120 volts, that's got 120 joules available to it. It drops off 120 joules with you, because it's 120, the voltage is 120 joules per coulomb, and you took a coulomb. You get 120 joules. Is that followable? Or questions about that? Yeah.
What quality makes the same amount of
what quality makes the same amount of charge have different amounts of energy? Well, a couple of important things. One is, suppose you have 1 coulomb and you put it on a tiny little marble. Now all the little charges, the little pieces that actually compose that 1 coulomb are very close to each other, but they really hate it. That's going to have a high voltage. They are desperate to get rid of it. On the other hand, if you spread them out onto a big ball, same charge, you let them get away from each other more. They aren't as unhappy. The voltage will go down. So if you just simply expand their territory, you let their voltage go down. Alternatively, is this true? If you bring negative charge nearby, it's basically, it's the, to not get into potential messes, it's the environment around the charge and how tightly the charge is packed. And we'll see there are other things that contribute to voltage too. But that's okay so far? Other questions? They're good questions. Thanks for asking them. Okay, yes?
Could you repeat what changed when you had the smaller area and the larger area?
If you take a certain amount of charge and you pack it especially tightly, that's an action that requires extra work. So suppose you had a squishable aluminum ball that you can fill with charge. We'll worry later about where the charge goes. And you did that by pushing charges little bits at a time onto it, and you have accumulated 100 joules of work to put 1 coulomb on this ball. So there it is, the ball sitting there with 1 coulomb of charge, and you did 100 joules of work to get it there. It's at 100 volts. If you now squish the ball to tiny, somehow, I don't know, not to be worried about, that takes more work. The voltage goes up further. You might get to 1,000 volts when you pack it tighter. Is that okay? The easiest way to keep cranking up the voltage on an object without changing the size of the object is just keep pushing more positive charges on it. But the other way is just change the shape of the object. All right. So that's the story of voltage. There's a complexity to this, though. And that is, there is such thing as a negative amount of charge. And how do you deal with voltage and negative? It's messy a little bit. So if all there were positive charge in the world, you could imagine that the more you pack positive charge together, the more energy you get per charge, and therefore it's all positive voltages. Life would be simple. That's all you got is positive voltages. Well, there are negative charges, and if you pack together negative charges, so I'm on a second ball over here, packing negative charges in. It still takes energy to do that. Grab a negative charge, shove it onto that ball. Grab another negative charge, shove it on. You're accumulating negative charge, and suppose you could accumulate an entire coulomb of negative charge, which is really, to say, a negative coulomb of charge. Minus 1 coulomb of charge. That activity took a lot of work. 100 joules of work again. So we have 100 joules of energy here, and that's possessed by minus 1 coulomb of charge. How did you figure out the voltage? You do the same as always. You divide the energy, 100 joules, by the charge, minus 1 coulomb, and you get minus 100 volts. That really is minus 100 volts. Large accumulations of negative charge have voltages that are below 0. They're negative rather than being positive. And how do you think about that then? To release this energy, you start letting negative charges leave. You let 1/10 of a coulomb sail off to the stars. In that process, it will release 10 joules. It will have followed all the rules. It had minus 100 volts. It's minus 100 joules per coulomb. You let off 1/10 of a coulomb. You got 10 joules out of it. The math all works out even though you're working with negative stuff. And as a general rule, we will see in the near future, if we stick to working with positive charge, which we will in many contexts, we will not worry about it's going through my head is this nasty choice, unfortunate choice that Franklin made of giving electrons negative charge. we will spend a lot of time worrying about how charge, generic positive charge, moves through things, ignoring the fact that there even are electrons. And if you let positive charge go from a region of high voltage, positive voltage, to a region of negative voltage, the positive charge loves this. It releases lots of energy. If you go from a ball that's at 100 volts, having, say, it had a coulomb of charge on it with 100 joules in it, that's 100 volts plus, and you got the negative version, 100 volts minus. In letting a coulomb go from the 100 volts positive, this is a coulomb of positive charge, it loves to leave that positive charge accumulation. It's really repulsive. And it loves to go over here to this negative charge accumulation because it's really attractive. So it releases 100 joules by the time it gets to 0 volts, which it actually will somewhere. It'll get to 0 volts around here. And then it'll go all the way down to negative 100. So the long and short of it is, charge loves to go from charge without the modifier charge. It's secretly positive charge. It's the usual rule. If I don't say negative, it's positive. So charge loves to go from high voltage to low voltage. It releases energy in that process. To go the other way, you have to do work on it. Push it all the way from low voltage to high voltage. If this doesn't all settle the first time through, it's okay. Come back to it over and over. One of the advantages of going through topics, doing physics topic by topic, is each topic often draws back to stuff we did for the last topic or the topic before that. So you get to revisit it. Any questions so far about voltage, the idea of voltage? It's one of these mysterious things that you've heard your whole life, but this is the real definition of it. Okay. So this is mostly asking you to tell me what I told you. We've got two surfaces, one with positive charge on it, one with negative. And if we pull them apart, what happens to the voltage of the positive surface? You okay with the question? How many think the voltage increases? How many think that it decreases? How many think it remains constant? Okay, you got a 50-50 split here. I'm asking about the voltage of the positive surface after all. You guys talk about it among yourselves for 30 seconds or something like that, and let's see where you can get. It's a 50-50 split between increases and decreases. Let's see if we can fix that. Okay, let's come on back here. So we got two surfaces, one positive, one negative. They were very close together. If we pull them apart, what happens to the voltage of the positively charged one? How many think its voltage will increase? How many think that the voltage will decrease? How about remain the constant? Okay, there are a few lingering people sticking with decrease. It is increase. And the reason for that is, as you pull these two apart, this takes work. Energy is going into the system. So both plates are accumulating more energy in the form of electrostatic potential energy. The positively charged plate has that energy owned by a bunch of positive charges. So its energy, it's got an increasing amount of energy per charge. Positive energy, positive charge. Life is simple. Its voltage is going up. More energy per charge. Okay? The negative one's the messy guy. It's accumulating more energy, but it's an accumulation of negative charge. So it's more energy per negative charge increase. Its voltage is going the wrong way. It's going down because you've got more energy divided by a negative amount. It gets more and more, a bigger and bigger negative quantity. I wish I could make that problem go away, but I can't. I mean, there is negative charge in the world, and it's around, and there are negative voltages. Is that okay? Any questions about that idea? Yes, Kristen.
So you're saying it was the opposite way. So say the voltage of the negative surface will.
The voltage of the negatively charged plate will decrease. It was probably already negative and it's going farther negative.
Yeah, okay.
Positive voltages are places that positive charge loves to leave. Negative voltages are places positive charge loves to go to, destinations. So it just as a rule of thumb, I mean, there'll be exceptions when you've got very complicated arrangements and stuff, but positive charge releases energy in leaving high voltage, and it releases energy in going to negative voltage. It loves to get there. Yes?
Does an object with 100 like positive voltage and an object with 100 negative voltage have the same number of joules?
There are two objects, one with 100 positive volts and one with 100 negative volts. Do they have the same number of joules? That is the same amount of energy present. We're not sure because it depends on how much charge is there. You can have a 100-volt object, positive 100-volt object, that has 1,000 coulombs of charge there, in which case it's sharing 1,000 times 100 joules of energy. It's got 100,000 joules of energy there. There's a lot of charge sharing it, so it's only 100 volts. And you have a little dimply thing down here that's just negative. It's only got a tiny fraction of coulomb, but it's got a good amount of energy. It can be minus 100 volts. But the net amount of energy not very high. Okay? And let's see, is this where I want to do this? Yeah. Okay. I'm leading up to this guy. The time's about right here. Okay. Why can some things lose their charge quickly? So you know from experience that if you leave the clothes in the dryer, assuming you forgot the dryer sheet, which makes things no fun to begin with, but if no dryer sheet, no fabric softeners and stuff, particularly winter day, you run the dryer, all the clothes are all clingy to each other, having accumulated lots of static charge. The net charge inside the dryer is probably pretty close to zero, but there are lots of, this one's positive, that one's negative, they're all happy and sticky. If you let them sit there for an hour, they gradually will lose that charge. And that's because if you have accumulations of, say, positive charge on some object, all the positive charges, the individual ones, and now I'm again thinking in terms of the little elementary fundamental pieces, the little electrons and protons, they're each repelling each other. It's in their best interest to leave. They would release energy in leaving. Things accelerate in the direction that makes them, that reduces their potential energy as quickly as possible. They want to leave. Same with the negatively charged ones. Basically, things love to go towards being electrically neutral. Their ability to leave depends on the ability for charge to move through materials. And just to give you a sort of a first glimpse at the idea of electrons and charges moving, the world can sort of be broken down into two major groups, the metals and the insulators. There's lots of detail, but metals are materials in which charge is easily mobile. So if you put positive charge at one end of a piece of metal, it will very quickly migrate down to the other end as well. Why would it do that? Because if you put a lot of positive charge at one end of a piece of metal, it hates being near it. Lots of charges near each other. They hate it. They would much rather go through the metal and spread out. It reduces their total potential energy to spread out, get farther away from each other. So a metal, you put charge on it, whew, it's all over the whole piece of metal in an instant. Not quite an instant, but close. An insulator is different. An insulator has no mobility of charges. If you put them on one end of the insulator, they sit there. They cannot move. There's no facility to carry them around. And to give you to show you this a little bit, so now I'm going to not worry too much about my official order of things. If you recall, this piece of Teflon steals electrons, which is negatively charged electrons, from the silk when I do this. Again, it's not the rubbing, it's the contact that matters, but I'm getting lots of contact this way. This guy's now all covered with negative charges. If I go over here to the ball here, which is connected electrically only to that vertical beam and a little pivoting beam there, we can zero it? Yeah, 3. This supposedly, yes, there we go. Up. It was there until I moved it. There it is. get this guy out of the way. And that guy too. All right. So now as I take the negative charges that I've accumulated, it's covered with negative charges, if I put them on here and transfer them to that ball and that metal stalk, you can see the little pivot moves away because everybody here is covered with negative charges. They all want to get as far apart as possible. And one way for them to get far apart is for that little pivot to swing away from the support. It's okay? So this can detect charge and, yeah, it's mostly a detector charge. If I let the charge, it's still on there. If I take it off, which I can do probably with just my hand, it goes onto me and I spread it all over the room. And we'll clean up later. What I just wanted to show you a couple things is if I put a metal extension, this is a piece of brass, onto that system, and I touch the top up here, the charge goes right down that metal, spreads out all over what's called an electroscope, and we're back in action. The point being, it's clear, it's easy to see that this thing allows charge to move through it. The sign of the charge, we're not worried about it, positive or negative, it doesn't really matter in the story. Another possibility is a piece of plastic, and now if I put charge all over the top, and it's negative charge, I put it all over the top up here, I really am putting it there. It's on there, no action out of the electroscope, because the charge can't move through plastic, not this plastic anyway. So the world sort of divides into electrically charged things and divides into metals, or what are more generically called conductors, electrical conductors, and electrical insulators. Okay, having done that, let me go back to, just put the simple ball on top. I've got a sort of question for you, and that is this. If I take a metal container, so there's basically a metal container, just like a open soda can sitting on a non-conducting stalk. If I take that metal container and I put electric charge in, on, all around, where will I find it if we go looking for it? So I probably have it as a question in my collection, but I'll sprinkle it on a little bit in the inside. Oh, sprinkle it. Now it's a metal can, and metal allows charges to move. Where am I going to find the charges? I think I do have it as a question. There it is. I'm going to go looking for it. I'm going to go looking for it using the electroscope as a detector. And I'm going to say it's either on the inside of the pot, or on the outside of the pot, or in both. Is that okay with the question? You okay with it? How many think that we'll find it only on the inside of the pot? How many think that we'll only find it only on the outside of the pot? How about on both? Okay, the majority are going for both. So let's give it a try. I'm going to make sure I haven't lost any here. Sprinkle, sprinkle, sprinkle. Sprinkle, sprinkle. Okay, here we go. To find it, I'll start with a ball with nothing on it, and I'm going to go looking inside the pot first. So I'm going to carefully go down through the top of the pot, touch the bottom, come back up. Nothing. There's no charge inside the pot. Let's try the outside of the pot. It's all on the outside. Is that okay? Why? It's because suppose there were a couple charges on the inside of the pot, and they look across the empty space between them, and they go, they're all like charges. They hate each other. I can get a little farther apart from you by going through the wall of the pot, which is metal, and hanging out on the outside. And they all move through the pot to get away from each other as far as possible. Inside is too close. They can do better. They can go on the outside. Is that okay? This effect is, you may well have heard that if you're in a lightning storm, or if an electrical cable lands on your car, something like that, when you're inside your car, you're safer than if you're outside the car. This is why. If some accident dumps a whole lot of electric charge on in around your car, which is sort of a metal can like this, that charge hates being near if it's like charge, it hates being close to itself. So it spreads out, and the farthest it can get away from it is to go to the outside. That's where it is. So if electric cable lands on your car, don't get out of the car. Let somebody come get the cable off of it if it's actually in contact with the car. As you leave, now you suddenly become exposed to that charge. It's on the outside. Is it okay? I mean, it's a real effect. I mean, I'm not, no games here. It's real. It really is on the outside. And that leads us to this. This is known as a van der Graaff generator. There are two of them here, actually. What it does is it uses dissimilar materials at the bottom, coming into contact, more or less, to develop a little bit of one charge on one surface, one on another. It's got a rubber belt inside, and the rubber belt, rubber like Teflon, loves electrons. It will steal electrons. That belt will end up with a little bit of negative charge on it because of this dissimilar materials problem. The belt runs by a motor, carries that charge up to the inside of a metal can, a ball, and touches there. And the charge comes off the belt and goes to the outside of the ball, just like the can. Make sense? And once it's there, the last thing it wants to do is go back inside, where all of, get closer to its like charges. It hates that. It accumulates on the outside. And the belt keeps going up, picking up charge at the bottom, doing work on the way up, which you can, some of these machines, you can hear it doing work. As the charge accumulates on the ball, it's going to be negative charge, alas, that's what it is. Negative charge up here. As the belt carries more negative charge up there, it does work on the negative charge. You can sometimes hear the motor straining, going, oh my gosh, I'm bringing more negative charge to that negatively charged thing. Anyway, it accumulates, by some standards, a lot of negative charge. It's not going to be a negative coulomb of charge, but it'll be a good dose of charge packed in a fairly small space, and therefore it'll have a fair amount of energy per charge. How much? About 100,000 or 200,000 joules per coulomb. So it's going to go, and it's negative, so it's going to be a negative 100 or 200,000 volts, something like that. So where's the on switch? On switch. Power. You keep getting new ones. I guess it's the... You can hear the snaps. So that's it. It accumulates negative charge to the point where the negative charge is so desperate to get off and spread out somewhere, it jumps right through the air to my knuckle. For some reason, knuckles are less. It's okay to get it in knuckle. I hate it in my fingers. Over the years, I've had lots of shocks. Okay, so clearly a lot of voltage. Can you hear the belt? Does the belt speed up as I do this? Slow down? Yeah, you can't tell really. Anyway, just to show you some of the things that you can do with this toy, right, is if I put something else on top like this, the negative charge will have something else to spread out onto. And once it does that, it'll spread out onto the little fronds. And they all, having negative charge on them, they repel each other and up they go. The snaps that you're hearing occasionally, I don't know where they're going. They may be shooting from the ball down to the base. It's hard to get these things. You have to keep them clean because there's so many ways in which the charge can escape if you're not careful. So that's one. What I'm doing right now is I'm letting the charge escape and go into the base and basically leave so it doesn't accumulate any. And when we get to things like people, so now the charge is accumulating. Of course, now I've lost I forgot to set this back to camera home. I always forget. Okay, so people have been wondering, what? Yeah, shock me again. All right. There. Okay, and that guy should probably take off on its, it's not gonna do it. Sometimes it just takes off like go, woo, off it goes, okay. All right. So now the more fun one, though, is people. And I cannot pick hair. There's just no way. I've learned from experience that it's unpredictable whose hair will go up. But the idea is this, that, and I can do without help, if I electrically insulate myself by standing on an insulator, plastic, and put my hand on the ball, and this is the part that I would help you with so you don't have to get hit by the ball. Now I'm accumulating charge along with, hey, it works. I know I turned out to be good today. So I'm accumulating negative charge as well, and so up goes my hair. That's probably the best I've done. Got to be good for something. So anybody else want to try to see how their hair will go? So once in a while we get, Gabby? Yeah, somebody who's got, again, I can't predict it. Obviously, people who have a crew cut, it's not going to be very fun. But so the idea will be this. Gabby will stand on that, on the plastic, and I'll discharge the ball. So there's no...
If your hair is in a ponytail?
Probably, if you can bear with it, take it out of the ponytail.
It's really messy today, guys. I'm going to keep you
All right. All right. So stand on the plastic, put your hand on the ball, and I'll let charge accumulate. And don't take your hand off until you're done, and then when you're done, you take your hand off and step on the ground, and the charge will leave through your feet. You shouldn't feel anything. Yeah, yep, go ahead, okay? And now let the charge accumulate.
Oh, wait, no, I feel it.
Do you feel, yeah. Can you give your head a shake? So, yeah, some of the loose hairs are like, you can see in the mirror, you can see that some of the loose hairs are up. Can I get over there with it? Let me see. He did give me, yeah, one. Yay, there you go. Yeah, okay? So now take your hand off and just jump back on the floor. And you're done. Okay? Somebody else? Somebody feeling lucky? Once in a while we get somebody who just goes up like a dandelion. Please. Also, come on down too. Yeah. And what better way to go into Friday, or go into the middle of the weekend, actually. And those of you who are not up for doing it during class, we can do it after class too. Yeah, wet might be okay. I have no idea what's the best. It's completely hit or miss. I've had people that were amazing and people that just did nothing. So stand on the plastic, put your hand on the ball. Just one. One's enough because you're just making electrical contact. Oh, I guess you can see yourself in the. You know? see. Now you're like minus 100,000 volts here. One thing not to do is don't go up to somebody while they're doing this and hold your finger out because they're very high, very low voltage. They'll shoot sparks at you. That is pretty. You're pretty good, yeah. All right. Thanks. So now step back and touch the ground. You're good. Okay, come in. Okay. Hand the ball. Okay. The loose hairs are up. Give your hair a shake to sort of loosen up the hairs so they.
Starting to.
Yeah. The other thing is that any sharp point, as we will see, lets the charge escape for interesting reasons. So sometimes you stand on there and you feel sizzle, like something right there is just sizzling.
Yeah, my shirt.
You could that's spraying charge into the air. Okay. All right. Thanks. Yeah. All right. We'll see you all on Monday.